In this video session, we will learn the concept of conditional joint probabilities. Bivariate random variables may also be conditioned in the same way as single random variables. So similar to a single random variable, conditional CDF, we will look into the conditional CDF for joint variables. Let me write down the equation. So in the single random variable case, you have x and probability of the event B intersection, but here you have two variables, that is x and y intersected with event B divided by probability of B. So this is your CDF for conditional joint variables. Yes, we will look into how PDF will come out. Yes, so your PDF will look something like this: x comma y with conditioning. You have to get partial derivative with respect to x and y. So this will give you your PDF, conditional joint PDF. Yes. Now what is event B for joint random variable case? The event B will have observation in both x-axis, y-axis. So basically it has observation in xy plane. So if this is your xy plane and this is your event B, this is your plane of event B occurring. So it has both values of x and y. And probability of B, how you will find? Probability of B you can find by integrating the x-axis with respect to x-axis and with respect to y-axis, your joint PDF dx dy. Yes, this is how you will get your probability of event B occurring. Now let's move on to find PDF using joint PDF, conditional PDF using joint PDF. For single random variable case, you have already seen. What do you get? Let me first write down for a single random variable case. Yes, so it will be easier to understand. X, I am leaving a bit of a space so I can edit it over there itself. X divided by P of B, and your x was belonging to B, 0 otherwise. This was your single random variable case, your conditional PDF with respect to joint PDF. Now for joint case, let me erase and make the changes right there. And in this case, both x and y should be within the event B limits. So I hope this equation is clear. Next, just the joint PDF, we saw how you can get marginal densities, that is PDF for y variable, PDF for x variable from your joint PDF. Similarly, you can get conditional joint PDF for marginal densities. I will write down the equation for that. So you want PDF for only y variable when event B occurs. Yes. Then you will integrate to the limits of B, that is on x axis. So this will be x comma y b dx. This is how you can find the marginal conditional PDF when you have conditional joint PDF with you. In the normal scenario, you used to integrate for all possible sample values for x variable, but here, since all possible sample values fall within the limits of B, you will integrate with respect to the limits of event B. Now, the next part is what will happen if you have a random variable x which has a single point, small x. That is what happens if your capital X is equal to x. To come to this point, we will start with taking a little bit of area dx. Yes, to come to this point, we will start with this. So let me write down. So what will be your B? This is your B. So your f y given event B, integration limits become x and x plus dx. Yes, and your conditional joint PDF with respect to du over here. Once you integrate this, how will you integrate this? For that, you will have to substitute this. So what does that give you? X plus dx. This equation is nothing but your joint PDF divided by probability of B. I hope you are understanding from where this equation came from. This, okay? So now this is nothing but once you integrate, you get fxy of x comma y dx divided by p of b, and here your x will belong to within the limits of b. Now the other part, what needs to be found out in this equation is p of b. So let's find p of b. We already know what are the limits of b. Yes, your x falls within x and x plus dx. So this is covering a bit of an area under dx. So x becomes a continuous random variable, and probability of continuous random variable is found by finding out the area it is covering. So the probability becomes integral x to x plus dx fx of x dx, which becomes fx of x dx. So let me substitute in this equation. Yes, so what do you get? Fy with event b fxy comma y dx, and we just now found out the probability of b fx of x dx. So here you can observe dx, right? When will your x converge to point x? When this dx becomes 0. So once your dx approaches 0, your capital X, once this dx approaches 0, implies your capital X will become equal to x, which is nothing but your event b. So once your x is equal to small x, that is a single point, your equation will look like this. Yes, now this you can also denote as just x. Why? Your capital X has converged or is equal to a point small x. Similarly, other way around, for variable x, you could write as x when event b is on point y, fxy x comma y divided by fy of y. This is equation 1 and this is equation 2. Remember these two equations. We will use it again for some other important observations. Yes, and this case, these two cases of conditional probability is often called as conditioning on a point. Yes, conditioning on a point. Why so? Because the conditioning event here is your x is equal to x, or for the other equation y is equal to y, because x is x and y is y. Now let's find out conditional PDFs for equation 1 and 2. We got marginal condition PDFs, now CDFs. Getting CDFs is easy. Yes, what did you do? Just like your normal CDF, from PDF you have to integrate from minus infinity to y, and you will use your marginal conditional PDF. Similarly, for variable x, the variables just interchange. U given y du. Yes, I hope CDF you have understood. Now coming to expectations with a given condition. So your conditional expectation is given as g1 of y given event b is x. So along with g1 of y, you use conditional PDF for variable y in the equation. Sorry, this is dy, because this is with respect to variable y and the condition says the event b, capital X, is equal to small x point. Similarly, for the other variable, let's take it as g2 of x given y minus infinity to infinity g2 of x x, let me write down that again, fx x given y dx. This is your conditional expectations. Now moving further, using these two equations and the PDF, we can find conditional means, variance and characteristic function. So let me write down for y. You know what will come for x variable. Yes. So this is conditional mean. You have the function as y along with your conditional PDF, marginal PDF to be more precise. Similarly, you have variance, integral from minus infinity to infinity. You have y minus mu y given x. Yes, because you need to use conditional mean to find conditional variance. Similarly, you can find the characteristic function for this, that is conditional characteristic function j omega minus infinity to infinity e power j omega y dy. Similarly, you can see how the conditional mean, conditional variance and conditional characteristic function for variable x might play out. Yes. So coming back to the equation 1 and 2, some important observation which we will make here is, let me write down that equation again, both 1 and 2. Y given x y divided by fx of x. Similarly, you have for x fy of y. So you can observe something. Yes, let me mark that down with a different color. So what can you conclude? Fy of y given x into fx of x has to be equal to fx of x given y into fy of y. You can observe this is similar to Bayes theorem. Yes, it is similar to Bayes theorem. And one more observation to make. What if your x and y variables are independent? We already know if they are independent, your joint PDF, let me write that down clearly, is nothing but product of individual PDFs. Yes, this is only if x and y are independent. What will happen if you substitute this in the equation 1 and 2 here and here? Let me just drag it down. So your fx of x will cancel out here and you are left with fy of y, and on this side fx of x. So let me write down. So if your x and y are independent, then your conditional marginal PDF is nothing but your marginal PDF. Similarly, it holds good for the variable x, that is fx of x. This is only if your x and y are independent. So yeah, that completes your concept for conditional joint probabilities. Thank you.